as a result, there's thousands of different node types. It's a very, very big grammar. And here's an example of a real abstract syntax tree. You can't really see it very well because this is a little blurry. But this is generated by rows. This is sort of just a picture of it. But this was actually a very small program that just has a main method and then another method that has a Fortran. Very, very simple. So you can actually see, I don't know, you probably can't read it, but the main method kind of starts right here, and then it's a very short main method, and then the for loop is kind of around here. So basically, each of these nodes will correspond with different things. Like there's a node for like if statements somewhere here, and there's nodes for variable references. And yeah, so the whole program is right there in the tree. So Compass is a Rose subproject written in C++, and its purpose is to automatically detect flaws and security vulnerabilities in software source code using static analysis. And this was a project that I actually worked on this past summer when I was a Department of Homeland Security HS STEM intern at Lawrence Livermore National Laboratory. So that's how I kind of got acclimated with Rose and started working on the Rose compiler in the first place. So this is sort of a continuation of that. And basically, so in Compass, there's each flaw that Compass can detect has a checker that corresponds with that flaw. So different checkers detect different flaws or security vulnerabilities or what have you. And it's a plugin-based interface, so you can turn different checkers on and off. So if you only want to detect like 2 or 3 types of things, you can just turn those on and turn everything else off. You can run Compass. And then any flaws that are found are reported to the terminal with line numbers and an explanation for what the problem was. But there's also a plugin that will pipe this into popular IDEs, such as like Emacs and Visual Studio and Eclipse. So you can actually get Eclipse to have this little squiggly red underlines that will tell you, oh, there's a memory leak on this line or something like that, which is pretty powerful. So it's a very, very large project. And so the visitor pattern is a design pattern commonly used to traverse and analyze trees in general, but also abstract syntax trees especially. And it's used in object-oriented programming. So, and it'll traverse an AST in O of n time, where n is the number of nodes. So it just visits each node once. And code is written sort of on a per node type basis. So you'll write one method for each like type in your tree, and that method will just handle everything that ever happens with that type. And that can be really confusing and difficult to write sometimes, especially with rows where we have tens of thousands of different node types. So the per node type code is actually all contained within this one sort of unified visitor class. And that encapsulates all the logic for some traversal you're doing. So in the case of Compass, each checker actually has its own visitor. And again, Rose has thousands of node types, so this can be awkward, or these can be really awkward to write. And the problem with each checker having its own visitor is that you'll end up retraversing the same AST once for every single checker that you run, which is just really inefficient because there's hundreds of checkers. But it would also be really awkward to try to merge all those checkers together. You'd have to do some kind of pre-compilation step, and that somehow keeps global variables from colliding, that sort of thing. And it would be pretty awkward. And this isn't just the case in Compass, it's actually frequently desirable in static analysis to perform many different analyses on the same abstract syntax tree. So that's a pretty common pattern. So it's something that should be optimized. So the Get-Descendants-by-Type problem, I define it as efficiently answering arbitrary queries of the form, given an AST node A and a node type T, find the list of all descendants of A that are of type T. So basically, if you have, let's say, you have an AST and you want to find all the function definitions in that AST, and for each of those function definitions, maybe you want to find variable references or something. So both of those problems are just kind of examples of, oh, I have some node, give me all the descendants of this node that are of some particular type. So if you have a particular function, you could do a Get-Descendants-by-Type kind of query and try to find, oh, give me all the variable references that are descendants that are in that function. And so my claim is that, at least for most visitors, especially the ones you encounter in static analysis, you can rewrite those just using a series of queries of this form. that's particularly true with like memory leak detection and stuff where you're doing sort of per function or per block analysis. But basically, it's a much more imperative and command-oriented way of thinking of things, because instead of just looking at all the types all the time and trying to write all these different methods that handle these different types, you're just saying, okay, give me all the function definitions. Now give me like the descendants of those that are variable references. Now give me some specific if-then statement. So it's like talking to a database, basically. It's much easier for humans to understand. So that's the Get-Descendants-by-Type problem. And then there's this existing library in rows called the AST matching library. And this provides a regular expression-like query language for finding nodes within a rows-generated AST. And it can also solve the Get-Descendants-by-Type problem. But it does many other things too, so that it supports much more powerful queries. But I found when I was working on Compass this past summer that 95% of our usage of the AST matching library was actually just doing Get-Descendants-by-Type calls. So my sort of claim is that if you can optimize that, then that would be a really sort of beneficial thing. And so we can, you can rewrite visitors using the AST matching algorithm, and usually you'll just have a lot of Get-Descendants-by-Type queries. The problem is, under the hood, the AST matching algorithm is just doing a standard AST traversal starting on the root search nodes. So if you're looking at starting at the root of the tree and you want to find all function definitions, it's going to look through the entire tree. And then, let's say, once you find one of those, you want to then look for variables in that function. It's going to look through that whole subtree again just to find those variables. So you end up with these overlapping traversals. You're retraversing the same area multiple times. And typically in static analysis, like most of these checkers have many, many nested queries. So you might retraverse the entire AST 5 or 6 times when you only need to actually traverse it once. So in terms of ease of use, AST matching is great, but performance-wise, it's worse than the visible pattern. It needs some improvement. So the problem, again, is we want to run a large number of unrelated analyses using an imperative query-based interface that only needs to perform a single traversal. And we shouldn't have to needlessly retraverse portions of an AST when confronted with nested queries. So AST matching solves the first problem, but then the second problem it's very slow with. So, and we can accomplish, my claim is that we can accomplish this by creating some sort of index of an AST and then do something with that index. So now I'm going to go into what that might look like. First we're going to sort of review some properties of depth-first search. So I'm sure a lot of you are familiar with depth-first search and how depth-first indices work. But basically, if you have a tree and you try to do a traversal where you always go for the longest possible leftmost path that you can get, so 0, 1, 2, 3, and then you would jump up to 4, 5 there, and then 6, and then 9. So basically, if you understand depth-first traversal, you can label all these nodes with different indices corresponding to the visitation order in that traversal. And so I was working with this for a long time, trying to figure out how we can efficiently get these descendants. And I realized that, let's say you're looking at some node like B here, and you want, you're just thinking about the depth-first indices of everything that's a descendant of it. Well, everything that's a descendant of B is going to have a depth-first index greater than B's depth-first index. So look, there's 7, and then all of its descendants are 8, 9, 10, 11. So that's helpful. And then they're also all going to be less than B's depth-first successor, which in this case is D. So the next, if we've traversed B and we've traversed all of the descendants of B, the next node we would traverse is D. So it turns out that if you sort of organize all the nodes in the AST in these sort of typed arrays, so you have one for all the A's, one for all the B's, one for all the C's, and these are arranged in depth-first order, you can actually just look for, okay, so let's say we want to find all the descendants of B, this B node that are of type C. So we can say, okay, Well, its depth first index is 7. So let's go over here to our array of C nodes and find where 7 would fit in. So it would fit in between 4 and 8. So that's the start of our region that we want. And then the depth first successor is D12. So we look for where 12 would fit in. It fits between 10 and 13. So that's actually, those are the two nodes we want. And lo and behold, C8 and C10 are the two C descendants of B7. So that's kind of the basic property that both of my algorithms rely on. There's two of them. I'm going to go over them in a minute. But that's sort of the intuition behind everything. And so I didn't think of any creative names. There's algorithm A and algorithm B. Very boring. So the first algorithm is kind of simple. It's basically you just perform a pretty normal depth first traversal. And as you're going, you actually just build this structure that we were just working on. So this is basically a hash table that maps node types to dynamic arrays of nodes. And for each node type, you'll have a dynamic array containing all the nodes of that type in depth first order. So there's nothing about that takes a particularly long time. So you can do that whole traversal still in linear time in the number of nodes. And it'll take up a linear amount of memory. So it's very efficient when you're generating this index. And then if you want, that's a typo. Those should be sub T. I don't know what's going on there. So if you want to then perform queries on this index, you would do a binary search for those two indices that we were working with before. So let's say you want to find, okay, where does B7 fit in? So we just do a binary search and figure out what the insertion index would be. So you just binary search and find, oh, it goes between C4 and C8, so that's the start of our region. And then do another binary search for 12, and it fits between there. So the time complexity just ends up being log of M sub T, where M sub T is the number of nodes of type T that are in the AST. So that's better than log of N, because it's going to be like a small fraction then in practice, but asymptotically it's still depending on the size of the AST. So it's really just kind of log of N. Okay, so then algorithm B is a little bit more complicated. So it's going to build a much bigger index. It takes longer to generate. And the structure kind of resembles that of algorithm A. We actually have the same hash table with dynamic arrays that we had before, but then we're adding this additional structure where we have a hash table that maps specific nodes to additional hash tables where each of those hash tables maps node types to these ordered pairs containing those depth first indices, those ranges that we found before. So I'll show you what that means in a second. But basically all we're doing is we're creating a bunch of hash tables that cache the results of those binary searches that we did for algorithm A. And the indexing algorithm is recursive also, because we're basically doing a depth first traversal. So now I'm going to try, looks like the spacing got messed up on this account, but let me see here. All right, that's unfortunate. I'll just do it from the bottom of the tree then. So basically, the idea is, if we go back to here, when we found sort of this number, so like 4, 10 or 4, 11 sort of represents this region of like all the possible C nodes. So we basically store in a hash table just all the possible regions that we have. So look at here. So basically, if the way this works is we kind of do a depth first traversal of the tree, and sort of recursively at the end we look at each child node, and because we're doing it depth first, you're actually doing this step after you've traversed all the children. So you look at each child node and you have a sort of region associated with each child, and that for each type. So those are basically going to tell you, so for example, if we're looking at A3 here, this is all in terms of where are the C nodes in this tree. So A3 here, the only C nodes that are descendants of A3 could be found 4, 5, because 4 is the depth first index of this node, and then we just use 5 to say that because we use an exclusive bound in a second. So, and then as you go up here, we have another C node that's depth first index is 2. So we kind of merge this this range with our previous the child range. So 4, 5 becomes 2, 5 because we have to include 2 in this range. And as you keep going up, you just keep bubbling these results up recursively. And the end result is that for every single node, you can just say, oh, what's the range of the C nodes that are descendants of this node, and you can know in constant time just by looking at that hash table. So I'm sorry that this slide got messed up. So also these got messed up. Okay, so everywhere there's a downward arrow, that's supposed to be a sub. So this is supposed to say O of so the time complexity of the indexing process is O of n times t average times c average. So we have essentially three variables in play here, and t average. This is why Apple is Apple messed up all of the formatting for all of my math equations. But anyway, so what this is supposed to say is t average is basically if you look at an arbitrary, an average arbitrary AST node, t average is the number of types of that node. So you basically just take the number of types that are descendants of every single node, and you average it. So you're going to get a kind of small number because leaves don't have descendants, so that'll sort of drive that number down. So that's what t average is, and then c average is just the average number of children that a node has. So that'll also be small because leaves don't have any children, and there's a lot of leaf nodes. So what you end up with is n times these two numbers that aren't really going to change with respect to n, because once you get up to an AST of a certain size, you have a finite number of types, and in practice, probably not going to. That's probably going to sort of stay at the same number. And same thing with average number of children. But it might vary a little bit, like on a per AST basis, but it's not going to change with respect to n. So really, it's just running in linear time, or linear time, and the memory complexity is slightly better. It's just O of n times t average. So we save a little bit of memory there. And then the query time, which did work, that's constant time because we're just doing a hash table. So, all right, no more messed up equations. So I took these two algorithms and implemented them in this Rose sub-project called NodeFinder that I created. And that basically consists of 1,156 lines of C++ code, and that's including like benchmarks and unit tests and stuff. And using this library, you can index an AST or any subtree of an AST using either of the two algorithms. And this summer, they're actually the Department of Energy is going to be trying to integrate NodeFinder into the main Rose source branch. So we're going to be trying to pass integration testing and that sort of thing. Hopefully, people are going to start using it towards the end of the summer. And it's also possible that it'll be added on as an optional optimization to the AST matching library. Because as long as you have simple queries that don't do anything other than Get-Descendants-by-Type calls, you could just use NodeFinder instead. So it might just automatically do that. And hopefully, this summer's batch of DHS HSTEM interns will actually be rewriting a lot of the compass checkers using NodeFinder. So that's what I'm pushing for. We'll see if they'll do that. And so I did a bunch of different benchmarks to sort of make sure that the time complexities actually match up with what happens in practice. The problem, though, is that we want to track sort of the performance of AST indexing with respect to like increasing AST size or complexity. And that's really hard to do because for any given program, you can just generate, okay, we can generate an AST for that program that has a certain number of nodes. But what if we want to have a bunch of successively larger ASTs. You're not just going to find that sort of out in the wild, nicely formatted for you. So I developed this little algorithm that actually takes an existing AST and it'll partition it into these successively larger pieces just by finding subtrees. And that will give you nice data that you can actually run benchmarks on and do graphs with. And I won't get into the details of the algorithm. It's not very complicated. And so for our benchmarks, we used the gzip compression library. We used the source code for that to generate an abstract syntax tree because we figured that would be sort of indicative of real-world sort of software. And we used the partitioning algorithm to break the AST up into subgroups of increasing sizes. And then we benchmarked the performance of both algorithms as well as the AST matching algorithm in a variety of different indexing and query scenarios. And the way we actually did these is for each algorithm, we just measured the number of iterations that algorithm was able to run within a given time frame. So we did a 5-second time frame because you end up with these really big differences in time complexity. So like algorithm B can do queries in constant time, and then like technically the AST matching algorithm takes linear time in the number of nodes in the tree. So that's a huge difference. So when you if you try to time these a different way, you get too big of a difference in the order of magnitudes of the numbers. So the best way to do it is just to see how many times can it do it in a 5-second span. And then you just divide by how long you ran it, and that'll give you the average speed that each algorithm ran in milliseconds. So here's the graph that we got for index building, and that might be confusing because the AST matching algorithm doesn't actually build an index. So what I'm doing here is I'm comparing the sort of like index traversal speed of the AST indexing algorithms with the just kind of raw traversal speed of the AST matching algorithm because it doesn't have any equivalent of indexing. And so what we get is, of course, algorithm B, because it has a rather large constant factor, is the slowest here. So higher means slower. And basically, and then for algorithm A and the AST matching algorithm, we see that algorithm A is just slightly faster than AST matching, and which is a little odd when you think about it. But the reason this is probably the case is the AST matching algorithm has some extra bookkeeping it has to do to support some of its advanced query features. So it's probably something to do with that. But so algorithm A is like very fast at indexing, and these are all linear though in terms of the number of nodes in the tree. So asymptotically, there's really no difference between these. But in practice, it's going to be faster indexing with algorithm A than algorithm B. So this is, I did a number of other benchmarks, but this is the other one I'm going to sort of discuss. So this is a doubly nested query. So that was one of those queries that I mentioned before where you have you start at the root node, you're like, okay, give me all the function and definition nodes. And then for each of those function definition nodes, give me all the if statements. And then for each of those if statements, give me all the variable references. So something like that where you have multiple layers of nesting. And that's highly typical of what you see in the compass check. So this is a good sort of benchmark to run. And what we have here is algorithm B, of course, performs queries in constant time. So it's already generated an index, and it's just doing lots of queries. So constant time is rather fast, so it's kind of just flatlining down there. You can't really see any difference between the axes. And then algorithm A, if you recall, is sort of logarithmic in terms of the number of nodes, but it has a really good constant factor because m sub t is smaller than n. It's a fraction of n, but it's still a fraction of n. So you see this kind of logarithmic curve with respect to the number of nodes in the tree. And then the AST matching algorithm is just super slow here. So it's retraversing all of these subtrees because each layer of nesting that we add just adds another level of complexity where the AST matching algorithm is going to have to revisit stuff again and again. So my conclusion, based on sort of these benchmarks, is that algorithm B is vastly preferable to algorithm A, and definitely to the AST matching algorithm, because only with algorithm B can we get constant time query speeds, And then in terms of indexing, all three algorithms are still linear in terms of the total number of nodes. So asymptotically, they're interchangeable for indexing, but then this one is an order of magnitude faster than the next best one. So algorithm B is definitely the one I recommend for use. And then just in terms of how easy to use these different things are, so I would claim that AST indexing is definitely preferable to using the AST matching algorithm. Well, because of the better performance, but then it's preferable to visitor pattern traversals in scenarios where you have lots of unrelated visitors, so like compass and that sort of thing, because you can just index the AST once, and then you don't have to traverse it ever again. You can just run all of your different compass checkers, and they'll be really, really fast with these constant time queries. One thing I didn't mention before that might be slightly confusing, you're probably wondering, so how can you return like a list of things in constant time as we do with algorithm B? So the way that actually works is if you look at one of those trees again. So we have those arrays, right? And so this would be the result for some query. So instead of adding these to a new array, we can actually just define using pointers in C++, like a new kind of pseudo array that actually is just backed by these elements. So we don't create new arrays, we just reference the existing arrays that we've already created during the indexing process. And as a result, we don't have to iterate over these. So that's why we get the constant time with algorithm B, because we can instantly just return this object. And that's nice, especially if you're doing some kind of analysis where you just want counts of nodes, so like how many descendants of this are some type. We can get that count immediately, and we don't have to actually iterate over the individual elements. And then both AST matching and AST indexing are preferable to the visitor pattern in terms of how easy it is to program these things. So that's pretty much my conclusion. And there's kind of two sort of potential applications I've explored a little bit for these algorithms outside of like compilers, obviously. It's kind of rare that there's something that would need this, because the problem is if you index some tree structure, you're going to need to, if there's any changes to it, you're going to have to re-index the entire thing because of how the algorithm is designed. So the only scenario where this would be useful would be if you have some highly static tree that has node types, which is a really rare scenario. But one scenario where that might happen is if you have a file system that doesn't change very often, and if you indexed that, you could, in constant times, like instantaneously, look at any folder and get the list of all files that are of an arbitrary type. So you could say, oh, give me all files on my desktop that are Word documents, and it would loop in the subdirectories too. And that would be instantaneous rather than using some sort of logarithmic time like it usually is. So it's just sort of a very niche kind of thing, but an interesting sort of application. And then there's probably similar things in databases where if you have some largely static hierarchical data, so possibly geographical data or biological data where you have classification systems and types. So like if you wanted to find all towns in the state of Connecticut or something, you could do that with an index sort of like this. But it's pretty rare that there's an actual application for this, but those are the And one sort of last thing that's just really beneficial about doing things this way is once you have this index, it's thread safe. So you can perform queries on as many different threads in parallel as you want. And you don't have to do new traversals. You can just do this one traversal and then tons of stuff in parallel. So it's a really sort of powerful thing about this. Do we have any questions?
You said that that your project would be useful for finding, say, the heartbleed virus or the heartbleed vulnerability before it ever happened. Can you go into a little bit more detail about how?
So basically, for example, Compass is a kind of thing that's been in development for a while, but there's other products like Clang, which I think is a lot more well established right now. And Clang works in a similar way. We have all these different checkers to check for different vulnerabilities. So one vulnerability you might check for is oh, you do a bound check on an array or you do stuff with it. and that's a basic thing you have to do in C, or somebody can do a buffer overflow attack, which just happens is how the heartbeat works. So if somebody had run even a basic kind of static analysis suite on the OpenSSL code, the bug was, they would have probably immediately detected this bug. But one of the reasons that people don't run these very often is they can be pretty slow. So what I'm trying to do with my research is make them easier to write and make the analysis faster. And I think I've accomplished that. Anybody else?
Okay, at this point, I would ask everyone to cooperate.